In this video, we're going to look at the processes that are used by the small intestine specifically for the digestion of fat. Now, although proteins actually involve the most chemical complexity in terms of breaking down, fats also have their unique challenges because of the fact that they do not dissolve in water, simply because their chemical structure is not suitable to that of mixing with water. In fact, there's a word that we use to describe this behavior. We say that fats and any other substances are hydrophobic. Now, if we derive the meaning of this word, hydro obviously means water, and phobic is the adjective form of phobia, which means fear. So fats as a hydrophobic compound are afraid of or fear water and therefore don't want to be anywhere close to it. This begs the question, how do we actually dissolve fats if part of the process is actually getting them to dissolve? Well, just because they can't dissolve in water doesn't mean that they can't dissolve at all, and we have your liver to thank for the solution to this, which is a greenish colored liquid that we call bile that acts as a solvent that is able to actually get fat to dissolve. Now, if we take a look at the chemical structure of a unit that makes up bile, this compound here is what we call a bile acid. Although when bile acids are mixed into water, they become bile salts. So whether bile acid or bile salt is used, these two are effectively interchangeable. Now, bile compounds, bile acids, and bile salts are what we call amphipathic compounds. Now, if we break this word down, you might recognize the prefix amphi as being the same prefix as in the word amphibian, referring to organisms that can live on both land and in the water. So amphi in this case meaning both, and pathic is derived from a Greek prefix pathos meaning to feel. So in this case, an amphipathic solvent like bile acids or bile salts are able to feel or connect with both water and fats. In fact, we can see it on their chemical structure here. This part here is able to attract to water, and therefore this is what we call the hydrophilic side, meaning this is the side that likes water, and this side here, for the most part, is the hydrophobic side. And when we look at how bile acids or bile salts actually work, they actually are relatively ingenious in their design. So we can see that the side of a bile acid or a bile salt that fears water is going to be attracted to a large clump of fat molecules or any other lipid that doesn't dissolve in water. And bile is going to use this hydrophobic side in order to pull the fat molecules away from each other in order to get them to break into smaller fragments, each of which is now more easily able to digest. Now, the fact that your insides are mostly made of water is not a problem for bile acids or bile salts, because water is able to attract to the other side, meaning that even though the fat molecules are not dissolved in water, they are dissolved by bile acids or bile salts, which in turn are dissolved by water. So it's dissolving within dissolving, if you will. So but this process shows how bile can actually dissolve any hydrophobic molecule, such as fat, by separating them apart into smaller clumps of individual fat molecules, making it more easy to digest. And this process is what we call the process of emulsification. And if we want to use the verb form of this word, the verb form is to emulsify. So when bile acids are used in order to separate lipid molecules, whether it be fats or cholesterol, away from each other, we say that bile acids emulsify lipids. So in terms of where bile actually comes from, as mentioned, bile is produced in the liver, but the bile that is produced in the liver in preparation for assisting with fat digestion is stored in this small organ underneath the liver that connects to the duodenum, which is what we call the gallbladder. And when the duodenum recognizes that fats are being pushed from the stomach into the duodenum, this sends a signal to the gallbladder, or rather the duodenum sends a signal to the gallbladder to contract and therefore push the bile that it has stored into the duodenum in order to help emulsify the fats that have entered the duodenum and therefore make it easier for the pancreas enzyme lipase to actually chemically break down a triglyceride into 3 fatty acids. So in the next video, we're going to look at one of the auxiliary functions of the small intestine in terms of how the small intestine produces its own auxiliary digestive enzymes to finish the process, before looking at how fats are transported throughout the body, given that fats don't mix well with water, but given that your blood is mostly water.